What if the most profound story of the universe isn't written in the blazing hearts of a trillion stars, but in the terrifying silence between them? We have spent our existence gazing upward, searching for light, for connection, for evidence that we are part of a grand, populated cosmos. We found it in sprawling cities of galaxies and incandescent rivers of gas, a luminous web of impossible scale. But in our relentless quest to map the whole of creation, we stumbled upon something else, a discovery so vast, so desolate, and so utterly defiant of our understanding that it challenges the very story of how everything came to be. It is a wound in the fabric of space-time, an abyss where there should be life. This is a journey not into the light, but into the deepest, most unsettling darkness we have ever known, a search for the meaning of an impossible emptiness. Our voyage begins in a place of reassuring familiarity, a spiral arm of a rather ordinary galaxy we call the Milky Way. From here the cosmos appears generous, even crowded. We see the soft glow of our neighbouring Andromeda galaxy, a cosmic twin rushing toward us for an embrace that will unfold over the next 4 billion years. Together with dozens of smaller dwarf galaxies, we form a small gravitationally bound family known as the Local Group. It is our celestial neighbourhood, a comfortable island of matter spanning a few million light years. But to grasp the true nature of reality, we must leave this home behind. We must pull back. As we accelerate away, our galactic home shrinks to a smear of light, a single brushstroke in a far greater masterpiece. The Local Group itself becomes just one point of light among thousands, all members of an even grander congregation, the Virgo supercluster. Here, 100 million light-years from Earth, the universe reveals its first layer of magnificent architecture. This is not a random scattering of galaxies. There is a structure, a design dictated by the invisible hand of gravity. We see galaxies not as isolated islands, but as glittering citizens of a metropolis drawn together into dense clusters, their gravitational fields overlapping, interacting and merging in a slow cosmic ballet. The Virgo cluster. The heart of our supercluster is a chaotic, beautiful hub of activity. Giant elliptical galaxies, ancient and golden, lord over the region, their immense gravity stripping gas and stars from smaller galaxies that stray too close. It's a place of creation and destruction, a gravitational crucible, forging the future of thousands of worlds. And looking out from this vantage point, we see that our supercluster is not alone. It is connected, a single node in a network of unimaginable proportions. This is where the true map of the universe begins to emerge, and we must now travel 1,000 times further still. We are now sailing through the Laniakea supercluster, our home on the grandest of scales, a breathtaking filigree of light and matter, stretching over 500 million light-years. What you're seeing now is the cosmic web. This is the fundamental skeleton of the universe. It is not a metaphor. It is the physical, observable reality of how matter has organized itself over 13.8 billion years. Imagine the universe in its infancy, a hot, near-uniform soup of particles. Tiny quantum fluctuations, imperfections infinitesimally small, created regions of ever so slightly higher density. Over eons, gravity, the universe's master sculptor, amplified these imperfections relentlessly. The denser regions pulled in more and more matter, starving the regions around them. The rich got richer, and the poor got poorer on a scale that defies imagination. What grew from those primordial seeds is the spectacle before you now. We are flying alongside a filament, one of the countless luminous tendrils that make up the web. It's a celestial highway, a river of dark matter and hydrogen gas flowing through intergalactic space. Along this river, like pearls on a string, galaxies are strung out, their light tracing the path of an invisible gravitational current. They are born here in the dense streams of this cosmic river, drawing from its flow the raw materials to ignite billions of stars. These filaments are the transportation networks of the cosmos, channeling matter from the emptier regions and feeding it into the great intersections where they meet. The journey along one of these structures is a sensory overload of cosmic phenomena. We pass through nebulae vast enough to birth 1,000 suns, their vibrant pinks and blues painting the darkness. We witness the brilliant flashes of supernovae, the death cries of massive stars that enrich the web with the heavy elements necessary for life. We see the serene glow of ancient galaxies, their star-making days long past, and the frantic, brilliant blue of young galaxies still in the chaotic throes of formation. These filaments twist and turn through space, sometimes stretching for hundreds of millions of light years, weaving a luminous tapestry that fills the observable universe. They are the threads. Where these threads intersect, we find the second major component of the web, the nodes. These are the great crossroads, the cosmic cities. Here matter has accumulated in such vast quantities that it has formed massive galaxy clusters, the largest gravitationally bound objects in the universe. A single cluster can contain 1,000 galaxies like our own, all swarming around a common centre of gravity bathed in an atmosphere of superheated gas that glows fiercely in X-ray light. To fly through a cluster like the Coma cluster is to witness the universe at its most intense, a cacophony of gravitational forces and high-energy radiation. It is a place of immense power, a celestial engine where the fate of galaxies is decided. These nodes are the brilliant, bustling hubs of cosmic existence. And there is a third, more subtle component, the walls. If filaments are the highways and nodes are the cities, then walls are the great plains of the cosmos. They are vast, flattened sheets of galaxies stretching for hundreds of millions of light years, forming the boundaries between the great empty spaces. They are less dense than the filaments, but are still rich with structure, containing countless groups and smaller clusters of galaxies. Our own Virgo supercluster is part of one such wall. From our perspective within it, the universe seems full, a continuous distribution of light. But this is an illusion, a local bias. The true nature of the universe is not just the structure, but the relationship between the structure and its opposite. The web is only half the story. The other half, the part we have so far ignored, is the emptiness that the web defines. These are the cosmic voids. They are the vast, underdense regions that the filaments and walls surround the spaces that were starved of matter as gravity pulled it into the growing web. Normally, these voids are a natural and expected part of the cosmic structure. Our models of cosmology, built on our understanding of gravity and the universe's expansion, predict them perfectly. They are the quiet countrysides to the web's bustling cities. They aren't truly empty. They are just sparsely populated, containing perhaps a few faint lonely dwarf galaxies or wisps of primordial gas. They are typically tens of millions of light years across, maybe even 100 million. They are the serene dark oceans that separate the bright continents of the superclusters. For decades, this was our picture of the universe, a beautiful, predictable balance between the something and the almost nothing. It was a picture that made sense. It was a picture that fit our data, our theories, our simulations. And it was a picture that was about to be shattered. Our journey must now continue pushing far beyond the familiar territory of Laniakea, beyond the neighbouring superclusters we have mapped and named. We are travelling now toward the constellation Bootes the Herdsman. But our destination is not a star or a galaxy within it. Our destination lies far behind the stars you see from Earth, in the deep intergalactic space, 1 billion light years away. As we travel, a strange feeling begins to set in. The universe is changing. The brilliant filaments that guided our path are becoming thinner, more tenuous. The great walls of galaxies seem to be receding, the luminous tapestry fraying at the edges. The density of galaxies, which had been a constant feature of our cosmic landscape, is dropping off slowly at first, and then with an unnerving speed. It feels as if we have left the metropolis of the cosmic web behind, passed through the suburbs, and are now entering a wilderness unlike any other. The background hum of the cosmos, the faint radiation, and distant light from countless galaxies is fading. A profound silence is descending. The few galaxies we now encounter are spectral and lonely, isolated worlds adrift in a growing darkness. They are evolutionary relics, galaxies that somehow formed in this desolate expanse cut off from the great rivers of matter that feed their cousins in the web. They are cosmic castaways, their light serving only to emphasize the immensity of the emptiness that surrounds them. We press onward deeper into this strange and barren territory. The last faint strands of the cosmic web are now behind us. There are no more filaments, no more walls, no more clusters. There is nothing. Absolutely nothing. We have arrived. We are now hanging in the heart of what scientists call the Bootes void. But the name, simple and clinical, does not begin to capture the reality of this place. This is not just a void. This is the void. An abyss of such monolithic scale that it renders all human comprehension inadequate. Before us lies a region of space 1.3 billion light-years in diameter. Let that number sink in. If our Milky Way galaxy were a single grain of sand, this void would be a chasm over 2 miles wide. Light itself, the fastest thing in creation, would take more than 1 billion years to cross from one side to the other. It is a volume of space so colossal that it should by all rights contain hundreds of thousands of galaxies. It should be crisscrossed by mighty filaments of dark matter and gas. It should be home to brilliant clusters and sprawling superclusters. It should look like the rest of the universe we have just travelled through, but it doesn't. We have found a few dozen galaxies here, faint and scattered like a handful of lonely lanterns in an abandoned continent. Based on the average density of matter in the universe, this region is missing a staggering amount of material. It is a phantom limb of the cosmos, a place where the universe failed to be born. The emptiness here is so complete, so profound, that if you were to place our own galaxy in the very centre of this void, we would not have known that other galaxies even existed until the 1960s. That is how isolated this place is. It is the definition of cosmic solitude. The feeling here is not one of peace, but of profound unease. It is a violation of a fundamental cosmic principle, the idea that on the larger scales the universe is roughly the same everywhere. The Boots void screams that this is not true. It is a statistical anomaly so extreme that it borders on the impossible. This is the central mystery we have come here to confront. How did this happen? How can a region of space this enormous be so devastatingly empty? The standard model of cosmology, the very theory that so beautifully explains the formation of the cosmic web, simply cannot account for a void of this magnitude. To create a hole this big through the slow, gentle pull of gravity over 13.8 billion years seems impossible. It would require some force, some event, some unknown physics that we have not yet even begun to imagine. It is as if you came across a desert the size of North America, with not a single mountain range inside it. You would know instinctively that some extraordinary process must be responsible for carving out such a feature. So it is with the Bootes void. It is a feature carved out of the universe itself, and we have no idea what tool was used. Its existence poses questions that strike at the heart of our cosmic origins. Is this a scar from the earliest moments of the universe, a gargantuan bubble in the fabric of space-time that was inflated during the Big Bang and never recovered? Could it be the work of some exotic form of dark energy, an anti-gravitational force that has pushed matter away on an unprecedented scale? Or does it hint at something even more profound, a sign that our understanding of gravity itself is incomplete? The Bootes void is not just an absence of matter, it is the presence of a question written in 1 billion light-years of darkness. It challenges us, it confounds us, and it invites us on a scientific detective story of cosmic proportions. To understand this void is to understand the forces that built the universe. It is a clue, perhaps the most important clue we have, to the deepest secrets of creation. And now, our investigation must begin. We must look for the fingerprints of the culprit sifting through the faint light from the void's edge, and the echoes of the Big Bang itself searching for an explanation for the greatest and most terrifying hole in the universe. What if the most profound discovery you could make was not of something, but of nothing at all? For centuries our quest to understand the cosmos has been a mission of addition, a grand cosmic accounting of stars, nebulae and galaxies. We have been cartographers of light, meticulously plotting every luminous point on our celestial maps, driven by an innate human need to fill the terrifying blanks, to leave no corner of the known world uncharted. We assumed with a comforting and almost childlike simplicity that the universe on its grandest scales was fundamentally consistent, a substance spread evenly like sand on a limitless shore. This wasn't just a hopeful guess, it was a cornerstone of modern cosmology, a principle of such profound importance that it was woven into the very mathematics we use to describe reality itself. They called it the cosmological principle, the elegant idea that from any vantage point the universe would look broadly the same. No special places, no privileged positions, just an endless democratic sea of matter, shimmering with galaxies from one horizon to the other. This assumption of uniformity was more than just elegant, it was necessary. It gave us a universe we could grapple with, one whose monumental complexity could be tamed by equations. It was the universe of Einstein's early theories, a place of serene, predictable order. He, like the physicists who followed him, envisioned a cosmos whose primary architecture was one of smooth, continuous fabric. Of course, we knew there were lumps. We saw stars clustering into the majestic spirals and glowing ellipses of galaxies. We saw galaxies themselves drawn together by their mutual gravitational pull into families, great clusters containing thousands of members, like glittering cities in the darkness. But these were thought to be local phenomena, mere ripples on the surface of an otherwise placid cosmic ocean. The prevailing wisdom held that if you just zoomed out far enough, all of this intricate detail would blur into a gentle, uniform haze. The universe, in its ultimate expression, was supposed to be simple. It was a belief we held onto with fierce intellectual conviction, for the alternative was a cosmos of such bewildering structure that it bordered on the incomprehensible, a universe that perhaps played by rules we had not yet even dreamed of. The first hints that this comfortable picture was profoundly wrong began to emerge not with a sudden cataclysm of discovery, but with the patient, methodical work of astronomers in the 1970s and 80s. Armed with increasingly powerful telescopes and new techniques to measure cosmic distances, they embarked on the most ambitious mapping project in human history. Their goal was simple: to move beyond the flat two-dimensional photographs of the sky and build a true three-dimensional model of the galactic neighbourhood. The key was a phenomenon known as redshift. By analysing the light from a distant galaxy, astronomers could see how much its wavelength had been stretched by the expansion of the universe. This stretching was a direct measure of the galaxy's distance from us. It was cosmic surveying on an unimaginable scale. And as the data points began to accumulate, a picture of the universe began to emerge that was anything but uniform. It was a revelation that would tear up the old maps forever. At the Harvard-Smithsonian Center for Astrophysics, a team led by Margaret Geller, John Huchra, and Valérie de Lapperron was meticulously plotting these redshifts, one galaxy at a time. Each data point represented years of work, a single pinprick of light on a celestial map that was slowly, painstakingly being filled in. They were creating a slice of the universe, a cross-section of the cosmos, to see how galaxies were truly arranged. The expectation was a random peppered scattering of points. What they found instead sent a shockwave through the astronomical community. The galaxies were not distributed like a fine mist. They were organised. They traced out enormous interconnected patterns, forming vast shimmering walls and long, delicate filaments of light that stretched for hundreds of millions of light years. It was as if the universe were a single colossal organism, and the galaxies were merely the luminous cells that traced its hidden nervous system. They called it the cosmic web. This discovery was revolutionary, a paradigm shift as fundamental as the realization that the Earth was not the center of everything. Our cosmos was not a simple homogeneous sea. It was a breathtakingly complex tapestry, a gravitational scaffolding of unimaginable proportions. The galaxies, it turned out, were not the main event. They were merely the foam on the crests of immense invisible waves of dark matter. In between these glorious structures, these celestial cathedrals of light, there were darker regions, areas with fewer galaxies. These were the voids. In the new model of the cosmic web, these voids were an expected feature, the natural gaps in the filigree pattern. They were the quiet countrysides between the bustling supercluster cities. The initial simulations that beautifully reproduced this web-like structure predicted these empty patches, suggesting they would be modest in size, perhaps a few tens of millions of light years across. They were an integral, understood part of the new cosmic geography. The universe was still a comprehensible place, just one with far more texture and drama than we had ever imagined. But one team of astronomers, driven by that same cartographic impulse, was about to push deeper into an uncharted quadrant of the sky. And there, in the quiet darkness, they would find something that wasn't on any map, a feature so vast and so empty that it would not just challenge the new model, but threaten to break it entirely. Robert Kirshner, a charismatic and respected astronomer at Harvard, was leading one such survey in the early 1980s, alongside his colleagues Augustus Oehmler Jr., Paul Schechter, and a young Stephen Schechtman. Their project was born of a simple, powerful curiosity. The cosmic web was a new frontier, and they were explorers eager to chart its expanse. They chose to point their telescopes towards a seemingly unremarkable patch of sky, in the direction of the constellation But as the herdsman. Their work was a grind, a slow and deliberate process of measuring redshifts galaxy by galaxy, night after patient night. The telescope would lock onto a faint smudge of light, its instruments would sip at the ancient photons for hours, and the resulting spectrum would be analysed to reveal the galaxy's distance. One by one, they were adding new points to the three-dimensional map, hoping to trace the continuation of the great walls and filaments others had found. They began plotting their initial results, expecting to see the familiar web-like pattern emerge from the data, but it didn't. As the survey pushed deeper into space, a strange and unsettling silence began to descend upon their data. They would aim the telescope at a region where they expected to find a galaxy based on the density of galaxies in surrounding areas, and they would find nothing. They would aim it at another spot, and again only the blackness of intergalactic space stared back. A troubling yawning gap was opening up in their map. At first they treated it as an anomaly, a statistical fluke, or worse, a systematic error in their own observations. The immediate reaction was one of professional doubt. Perhaps there was something wrong with the instrument, a subtle flaw in the photographic plates or the electronic detectors. They recalibrated, they double-checked their calculations, they questioned their own methodology. The universe was simply not supposed to have holes this big. It was like drilling for oil and after passing through the expected geological strata, suddenly finding a subterranean cavern 100 miles deep. It felt unnatural, a violation of the established rules. The team pushed on their curiosity, now tinged with a growing sense of unease. They expanded the survey area, probing the boundaries of this strange emptiness. With each new observation, the hole grew larger. It was not a small pocket, it was a chasm. The data pouring in from the telescopes at Kitt Peak and Las Campanas was relentless and unambiguous. For a vast stretch of cosmic real estate, the universe appeared to have simply run out of galaxies. The few they could find were either on the near edge of this region or far, far beyond it on the other side. In between lay an abyss of almost perfect nothingness. The team's initial disbelief slowly curdled into a staggering realization. This was not an error. This was a discovery. They had stumbled upon a structure, or rather a lack of structure, of such monumental scale that it dwarfed every known void by an order of magnitude. It was a cavern in the cosmos stretching nearly 330 million light-years across. If our own Milky Way galaxy were at its centre, we would not have even known other galaxies existed until the 1960s. The light from our nearest galactic neighbours would still be on its journey towards us, traversing a darkness more profound and more complete than anything humanity had ever conceived. When Kirshner and his team published their findings in 1981, they did so with the cautious, understated language of scientific inquiry. But the implications were earth-shattering. The paper, titled "A Million Cubic Megaparsec Void in Boötes," sent a ripple of shock and skepticism through the global astronomical community. The scale of it was simply preposterous. The Boötes void, or as it was soon nicknamed, the Great Nothing, was so enormous that it posed a direct and profound challenge to the very theories that had just given birth to the cosmic web. The standard model of cosmology, which relied on the slow, steady pull of gravity acting on primordial fluctuations of dark matter, was remarkably successful at creating a web-like universe. Computer simulations could grow beautiful galactic filaments and modest voids over the 13.8 billion years since the Big Bang. But those same simulations could not under any normal circumstances produce a void of this gargantuan size. There simply hadn't been enough time. To excavate a hole this big, you would need to somehow move matter out of the way on an impossibly efficient scale, like a cosmic bulldozer working faster than the laws of physics seem to allow. The discovery ignited a firestorm of debate. Some astronomers insisted it had to be an observational bias, a misinterpretation of the data. Others, accepting the reality of the void, scrambled to find an explanation. Wild new theories began to circulate. Perhaps exotic forms of energy were at play pushing matter apart. Perhaps our understanding of gravity on these immense scales was fundamentally flawed. The Boötes void was more than just a curiosity. It was a monster. It was an inconvenient truth that sat squarely in the middle of our best cosmological models refusing to fit. It was a feature on the map that the mapmakers could not explain. The quest was no longer just about filling in the blanks. The discovery of this colossal emptiness transformed our understanding of the universe's structure, revealing that the story of the cosmos is written not just in the brilliant ink of starlight, but also in the vast silent paragraphs of nothingness. The Great Nothing was not an absence of a story. It was the beginning of a new one, a profound and unsettling mystery that beckoned us to look deeper into the dark to understand the forces that build the universe by first understanding what it is that hollows it out. The search for answers had just begun. A discovery of this magnitude is not met with quiet acceptance. It is met with a storm of professional skepticism, a barrage of probing questions, and an urgent, almost primal need for verification. The initial maps sketched by Kirshner and his team were revolutionary, but they were also drawn with a pencil not yet etched in stone. They were built from a mere 240 galaxies, a tiny sample size, when trying to comprehend a structure that could swallow our own supercluster whole. To the wider astronomical community, the claim was simply too extraordinary. A void was one thing. The cosmic web was known to be porous, a filigree of matter and space. But a chasm stretching for hundreds of millions of light years, an emptiness so profound, it bordered on the absolute felt like a violation of cosmic reason. It strained the very fabric of our understanding. The prevailing models of the universe, rooted in the elegant mathematics of the Big Bang, predicted a certain lumpiness, a certain texture to reality. They allowed for voids, yes, but as bubbles in a cosmic foam, not as colossal wounds. This Great Nothing, in the constellation of the Herdsman, was an anomaly of such breathtaking scale that it threatened to unravel everything. If it was real, our universe was far stranger, far emptier, and perhaps far more violent in its formation than we had ever dared to imagine. The gauntlet had been thrown down. The scientific imperative was clear to return to that patch of sky, to stare deeper into the abyss, and to map its shores with unwavering precision. What followed was not a single heroic expedition, but a slow, methodical siege. A new generation of celestial cartographers armed with more powerful instruments and more sophisticated techniques embarked on one of the most ambitious surveying projects in history. This was not a task for a single telescope or a single night of observation. Confirming the void required a brute force approach, a cosmic census on an unimaginable scale. Astronomers needed to measure the distances to thousands, then tens of thousands of galaxies in and around the suspected region. The key to this monumental effort was the redshift, the subtle stretching of light from distant objects as the universe itself expands. Like the Doppler shift of a passing siren, a galaxy's redshift reveals its velocity away from us, and by extension, its distance. Each measurement was a single vital data point, a pin placed on a three-dimensional map of the cosmos. Early efforts like the CFA Redshift survey began to fill in the blanks, and with each new data point the picture grew more alarming. The emptiness was not an illusion. It wasn't a trick of the light or a misinterpretation of sparse data. The void was undeniably there, and it was immense, but to truly grasp its terrifying dimensions, science needed a new weapon. That weapon arrived in the form of robotic multi-object spectrographs and dedicated deep sky surveys, most notably the Sloan Digital Sky Survey, or SDSS. Imagine a telescope that doesn't just look at one star or galaxy at a time, but can simultaneously measure the light from hundreds of them at once. At the heart of the SDSS telescope was a precisely engineered metal plate drilled by a robot with hundreds of tiny holes. Each hole corresponded to the exact position of a galaxy in the sky. Optical fibers plugged into these holes by hand in a delicate nightly ritual acted like tiny straws, sipping the ancient light from each target and feeding it into a spectrograph deep within the observatory. Night after night, year after year, this digital eye scanned the heavens, methodically dismantling the sky into its constituent parts, building a public library of the cosmos, one galaxy at a time. When this unprecedented mapping power was turned toward the Boots region, the true nature of the void began to resolve itself with horrifying clarity. The initial estimates were not just confirmed, they were found to be conservative. The void was bigger than first thought. Much, much bigger. As the data cascaded in creating a digital ghost of a vast slice of the universe, the emptiness grew from a startling anomaly into a monolithic feature of the cosmic landscape. Imagine scrolling through this three-dimensional map. You fly past the intricate tapestry of the Virgo supercluster, our own cosmic neighborhood, teeming with spiral and elliptical galaxies, a vibrant metropolis of stars. You push deeper past other clusters and filaments, the great highways of the universe. And then, nothing. The map goes dark, the pins vanish. For a distance that defies any human scale of comprehension, the universe simply stops. You are now crossing the great void. To traverse it at the speed of light would take you over 300 million years. Our entire Milky Way galaxy with its hundreds of billions of stars would be but a speck of dust lost within it. The final confirmed map revealed a roughly spherical region of space, an underdensity so extreme that if our galaxy were at its centre, we would not have known other galaxies even existed until the 1960s. The night sky would have been a profoundly lonely place, a field of stars set against a backdrop of perfect featureless black. This confirmation sent a profound shockwave through the world of cosmology. It was a direct empirical challenge to the standard model of cosmic evolution, a framework known as lambda cold dark matter or lambda CDM. This model, our best working theory for how the universe came to be, was incredibly successful at explaining the large-scale structure we see. It told a story of tiny quantum fluctuations in the infant universe stretched to astronomical sizes by a period of rapid inflation. These fluctuations acted as seeds, gravitational anchors, around which matter, both normal and dark, began to clump together over billions of years. The result, according to the countless computer simulations run on this model, should be a magnificent sponge-like structure, the cosmic web. Dense galaxy-rich filaments and massive superclusters are woven together surrounding less dense, emptier regions, the voids. Lambda CDM predicted voids. It needed them. They were an essential part of the cosmic architecture, but the theory also placed limits on their size. The simulations could produce voids of tens of millions of light-years across perhaps even 100 million. They were the natural gaps in the web, the quiet suburbs of the cosmic city. The Bootes void was not a quiet suburb. It was a continent-sized hole where the city should have been. According to the statistical probabilities of the lambda CDM model, a void of this magnitude was a near impossibility. It was a 6 sigma event, a statistical outlier so extreme that finding it was like finding a human being who was by sheer chance 20 feet tall. The simulations could not build it. They would run for weeks, evolving billions of years of cosmic history, and they would create beautiful, intricate webs, but never a hole this large. It was as if you asked a forest to grow, and it followed all the rules of biology but left a perfectly circular, 1,000-mile-wide clearing in its heart for no reason at all. This presented cosmologists with a deeply uncomfortable trilemma. Either our understanding of the universe's initial conditions, the seeds of all structure, was flawed, or the very laws of gravity as described by Einstein behaved differently on these colossal scales. Or perhaps there was some other unknown physical process at work, some titanic force in the early universe capable of bulldozing matter on a scale we had never conceived. The Bootes void was no longer just a curiosity, it was a crisis. It was a silent, empty accusation suggesting that our most cherished theories of the cosmos were at best incomplete. The search for answers became one of the most pressing quests in modern astronomy. Scientists scoured the void not for what was there but for what wasn't, hoping the very character of its emptiness held a clue. They looked for faint traces of primordial hydrogen, for the gravitational lensing of dark matter, for any signpost in the dark. And in doing so, they stumbled upon something even more perplexing. Something that didn't fit the narrative of a perfect, sterile emptiness. Deep within the heart of the void, where nothing should be, they found something. They found galaxies. The discovery was as subtle as it was profound. It didn't come with a flash of light, but through the patient sifting of enormous data sets. An astronomer named Greg Aldering and his team were meticulously analysing the data, pushing their instruments to the absolute limits of their sensitivity. They were looking for anything at all inside the void's vast interior, and there, hidden in the statistical noise, were a few impossibly faint smudges of light. At first, they could have been errors, cosmic ray hits on the detector, instrumental glitches, or distant background galaxies shining through by chance. But follow-up observations, painstakingly acquired, confirm their nature. They were not background objects. Their redshifts placed them squarely inside the Great Void. They were inhabitants of the emptiness. Initially only a handful were found, 8 galaxies, then a few dozen more were unearthed by later surveys. As of today, we have catalogued around 60. 60 galaxies in a volume of space that should by rights contain well over 2,000. It is the most sparsely populated region of the known universe, a celestial ghost town with only a few lonely homesteads remaining. Meeting one of these void galaxies would be an unnerving experience. They are not like the grand spirals or stately ellipticals we see in our crowded cosmic neighbourhood. Many of them are peculiar, almost misshapen. They tend to be smaller, bluer, and burn with a more furious rate of star formation than their counterparts in the wider universe. One of them, a strange cigar-shaped galaxy designated MCG Plunzul 10215, looks like a celestial blowtorch, a brilliant tube of gas and stars shining in profound isolation. These galaxies are cosmic castaways island universes adrift on an ocean of black. From a planet orbiting a star within one of these galaxies, the view would be one of breathtaking desolation. Your own galaxy would be a river of light across the sky, a familiar home, but beyond it there would be almost nothing. No Andromeda to gaze upon, no Magellanic clouds, no faint smudges of distant galactic clusters, just an endless, unpunctuated darkness, a void so complete that the very concept of a universe beyond your own would seem like a mad fantasy. You would be utterly terrifyingly alone. This discovery did not solve the mystery of the Bootes void. On the contrary, it deepened it, adding a rich new layer of complexity to the puzzle. The void was not entirely barren after all. It was a unique cosmic frontier sparsely populated by a handful of strange survivors. And these survivors immediately raised a new set of tantalizing questions. How did they get there? Are they vestiges of a structure that was somehow erased? Did they form in place from the incredibly tenuous wisps of gas that must thread even this empty space? Or were they somehow shot into the void, ejected from the cosmic web by some ancient violent gravitational encounter? Their strange shapes and vigorous star formations suggest they are living different lives from the galaxies in our part of the cosmos. Without the constant gravitational nudges, mergers and gas stripping that come from having neighbours, they have evolved in near-perfect isolation. They are a control group for galaxy formation, a laboratory for studying what happens when you raise a galaxy in utter solitude. These lonely islands of light were not just statistical oddities, they were witnesses. They are the only material clues we have from inside the great emptiness itself. Their chemical composition, their motion, their very existence holds the key. But what had they seen? What cataclysmic force could have sculpted this monstrous cavity in the fabric of reality, sweeping their entire cosmic neighbourhood clean of all but a few ghostly occupants the answer scientists began to suspect could not be found in the present day? To understand the origin of this great cosmic scar, we would have to look back in time, back to the universe's chaotic infancy, to an era of unimaginable energies and forces that laid the very foundations of the cosmos we see today. The void was not just a hole in space, but a fossil record of creation itself, and so the map was drawn, but the silence it depicted was deafening. Every survey, every painstaking redshift measurement only served to deepen the wound in our cosmic theories. We had stared into the heart of the Bootes void, an abyss so profound it seemed to defy the very principles of cosmic structure formation. For decades, our approach to cosmology had been one of photons and lenses of capturing ancient light to piece together a portrait of the universe. Yet the portrait was now marred by a gaping hole, and more light, more observation wasn't providing an answer. It was only making the question louder, more insistent. The tools that had revealed the grand tapestry of the cosmos were powerless to explain its most terrifying omission. A profound shift was necessary. If looking out into space could not solve the riddle, perhaps the only path forward was to look inward, not into our own minds, but into the concentrated, accelerated universe of a machine. The age of observational astronomy in this one profound instance had to seed the stage to a new kind of exploration. A journey not through space but through time itself, guided by the cold, flawless logic of a supercomputer. We had to build the universe from scratch, not with stars and gas, but with data and algorithms. This is the domain of computational cosmology, one of the most ambitious scientific endeavours ever conceived. Imagine trying to reconstruct the entire history of a continent, from the first continental drift to the rise of mountains and the carving of rivers using only the laws of physics. Now scale that ambition up to encompass everything we know. Inside the humming racks of a supercomputer, scientists create what they call a universe in a box. It is a digital genesis, a self-contained cosmos born from a handful of fundamental ingredients. You begin with the seeds of creation, a vast but finite number of points, each representing a colossal mass of dark matter, the invisible scaffolding upon which galaxies are built. You sprinkle in the laws of physics, the non-negotiable rules of the game. Gravity, elegant and relentless in its simplicity, is the primary sculptor commanding these points to pull on one another. Then you add the universe's most mysterious component, the ghost in the machine dark energy. This is the force of expansion, an inexorable gentle pressure embedded in the fabric of space-time itself, pushing everything apart. With these ingredients loaded, the simulation begins. The cosmic clock is set to just after the Big Bang, a time when the universe was an almost perfectly smooth, dense fog. The computer then calculates the gravitational pull and the outward push on every single particle, moving them a tiny fraction, just a single step forward in cosmic time. Then it does it again, and again, millions of times, billions. A single simulation can run for months, consuming more electricity than a small town as it crunches the numbers for trillions upon trillions of interactions. You're witnessing an accelerated evolution, a 13.8 billion year cosmic saga, played out on a timescale you can comprehend. What starts as a near uniform haze begins to curdle. Gravity, the great amplifier of imperfections, finds the very slightly denser regions and makes them denser still. Filaments of dark matter begin to coalesce like strands of a celestial spiderweb. Where these filaments cross, matter piles up into dense tangled knots, the future sites of massive galaxy clusters. And in the spaces between where matter has been stolen away by the gravitational pull of its neighbours, voids begin to open up. These simulations were a breathtaking triumph. For the first time we saw the cosmic web emerge not as a static image but as a living, breathing structure. It looked for all the world like the universe we saw through our telescopes. But here in this digital creation, the ghost of the Buddhist void returned to haunt us. The simulations were magnificent, producing a universe teeming with structure, a universe that felt right. They created voids, thousands of them, which was a spectacular confirmation of the theory. These were the natural expected outcomes of gravity and expansion working in tandem. There was just one gigantic problem. They were all too small. The virtual universes blossoming within our most powerful machines had an upper limit to their emptiness. They could produce voids 50 million light-years across perhaps even 100 million. These were impressive, but they were the cosmic equivalent of ponds and lakes. Our telescopes had found an ocean. The Buddhist void at 330 million light-years in diameter simply refused to form. It was an outlier, a statistical impossibility, that our best digital universes could not replicate. The models that so perfectly painted the intricate lace of the cosmic web failed to produce its most shocking feature. This was a crisis, a moment of profound doubt. It suggested that our understanding wasn't just incomplete, it was fundamentally flawed. We were missing a key piece of the puzzle, some dynamic process that could take the universe we thought we knew and tear a hole in it larger than anything we had dared to imagine. The breakthrough came, as it so often does, not from a new piece of data, but from a radical new perspective. We had been thinking of voids as passive structures, as the leftovers of creation. They were the empty spaces on the cosmic dinner plate, after gravity had feasted on all the available matter. We saw them as absences defined only by what they were not. But what if that was profoundly wrong? What if a void was not just a lack of something, but a thing in itself? What if it was an active agent in the cosmic drama, a force to be reckoned with? The key lay in the delicate universe-spanning tug-of-war between gravity and dark energy. On the dense filaments of the cosmic web, gravity is king. It pulls matter together, binding galaxies into clusters, fighting against the relentless expansion of space-time. But inside a void, the situation is reversed. The density of matter is so low that gravity's grip is extraordinarily weak, almost non-existent. In this rarefied environment, dark energy, the gentle uniform push of cosmic expansion, has no meaningful opposition. This subtle imbalance changes everything. It means that the space inside a void is expanding slightly faster than the space within a dense filament. A void isn't just an empty region, it is an emptying one. It acts like a cosmic high-pressure system exerting a subtle but inexorable outward force on its boundaries. Think of it as a celestial snowplow. It sweeps up the thin wisps of matter on its interior and shepherds the galaxies on its edges, pushing them away, piling them up onto the surrounding walls and filaments. This process creates a feedback loop. As the void pushes matter out, it becomes even emptier. As it becomes emptier, gravity's influence weakens further. As gravity weakens, dark energy's dominance grows and the void expands ever faster, its influence growing with each passing billion years. Voids were not passive gaps. They were dynamic, growing and shockingly powerful engines of cosmic architecture, actively sculpting the universe around them. This was the missing piece of the puzzle, the hidden dynamism that our earlier, simpler models had failed to capture. The silence of the void wasn't the silence of a vacuum, it was the quiet, patient work of a universe-shaping force. This revelation that voids could grow and expand opened the door to an idea as elegant as it was startling. If voids are active and expanding, what happens when two of them meet? The answer provided the first plausible origin story for a monster like the Buddha's void. Scientists began to theorize about a process they called void merging. Imagine the surface of soapy water covered in a foam of bubbles. Small bubbles are unstable. Their high surface tension pushes them to collapse or merge with their neighbours. Over time, you see the foam evolve. Small bubbles disappear, and their volume is absorbed into larger ones. The thin, soapy walls between adjacent bubbles pop, and two become one, then three, then four, coalescing into a single dominant superbubble. This cosmologist proposed is precisely what happens in the universe. In the early cosmos, the cosmic web was populated by a multitude of smaller, relatively modest voids, the standard-issue voids our first simulations had produced. But these voids weren't static. Each one was its own expanding bubble of space-time. As the universe aged, these neighbouring voids began to swell, pushing against one another. The walls of galaxies that separated them, once distinct and stable, found themselves caught in a cosmic vice, pushed from both sides by the relentless expansion of the voids. Eventually the pressure becomes too great. The wall, the filament of galaxies separating two voids, is torn asunder. The galaxies that once formed this boundary are violently swept away, bulldozed onto the outer edges of the newly formed larger structure. In a moment of cosmic reorganization, two pockets of nothingness become one. The barrier vanishes and a new larger void is born from the confluence of its parents. This process, a cascade of emptiness, would repeat over billions of years. A small void would merge with a neighbour, creating a medium-sized one. This new void, with its greater expansive power, would then encroach upon another, swallowing it as well. The Boots void in this new and dramatic telling was not born a giant. It grew into one. It is not a single primordial emptiness, but a composite entity, a megalopolis of nothingness built from the ruins of hundreds of smaller voids that have popped and merged over the entire age of the universe. It is a scar left by a history of cosmic cannibalism, where emptiness consumed emptiness to create a void of unimaginable proportions. This was no longer just a hole, it was an artifact, a structure with a violent and dynamic past written into its very fabric. Armed with this powerful new hypothesis, scientists returned to their digital universes. They rewrote the code, refining the physics to more accurately model the subtle but powerful effects of dark energy inside low-density regions. They seeded their virtual cosmoses with the initial conditions prescribed by our best measurements of the Big Bang's afterglow and pressed run. Then they watched. For months, the silicon oracles churned through the eons, and on the screens a new story unfolded. The familiar cosmic web began to form, but this time it was different. It was more alive, more violent. The voids were no longer placid lakes, but churning, expanding oceans. The teams watched mesmerized as small pockets of rarefied space began to swell. They saw them drift through the simulation box, their boundaries pressing against each other, and then they witnessed it. They saw a thin filament of digital galaxies, a wall separating two growing voids begin to stretch. It thinned, buckled, and then snapped. The galaxies that had made up the wall were flung outwards at incredible speeds, like debris from an explosion, as the two voids merged into a single elongated and far larger entity. The simulation continued to run, and the process repeated itself again and again. It was a chain reaction of coalescence. The newly merged void, now larger and more powerful, would encounter another and consume it, growing larger still. What emerged was a universe with a far greater range of structures than ever before. It had the small common voids, but it also had a population of rare colossal supervoids that had formed through this hierarchical merging. After billions of years of simulated time, the cosmologists zoomed in on the largest empty region their new universe had managed to create. They measured its dimensions, tracing its boundaries across the screen, and for the first time the numbers aligned. The simulation had spontaneously and naturally produced a void on the scale of Boots. It was no longer a statistical fluke, it was an inevitable if rare consequence of the fundamental laws of our universe playing out over cosmic time. The monster had been caged. We finally had a plausible explanation, a creation story for the great nothingness. The emptiness that had once symbolized a profound gap in our knowledge now stood as a testament to the beautiful, violent and dynamic interplay of gravity and expansion. But in solving one mystery, we had opened the door to another. If the Boots void is the result of such a colossal and energetic process, a multi-billion-year history of cosmic mergers, then it cannot be a passive feature of the landscape. An object of this scale, a structure with such a violent past, must leave its mark. It is no longer just a hole in the distribution of galaxies. It must be an active gravitational and cosmological engine. What does this expanding supervoid do to the galaxies that live on its edge? How does its immense negative presence, this anti-structure, warp the very fabric of space-time around it? And could its colossal shadow be seen elsewhere, perhaps imprinted on the faint ancient light of the cosmic microwave background, the baby picture of the universe itself? The void was no longer just a place to be explained. It was a place with consequences, a cosmic actor whose influence might just stretch all the way back to the dawn of time. Our journey into the void was far from over. We had only just begun to understand the power of its emptiness. But to imagine these colossal voids simply drifting into one another, coalescing like soap bubbles on the surface of water, is to fundamentally misunderstand the scale of power at play. Their merger is not a passive accident of cosmic proximity. It is an active and violent expulsion, an eviction, on a scale that defies all human intuition. This process is driven masterfully and terrifyingly by the most enigmatic and pervasive force known to science, a force that acts as the silent architect of cosmic emptiness. We call it dark energy. It is the ghost in the universal machine, an invisible, inexorable pressure embedded within the very fabric of space-time. To truly grasp what is happening inside the Boots void, you must first unlearn a core assumption about the universe. For centuries we looked to the heavens and saw a grand cosmic ballet governed by one undisputed master, gravity. Gravity, the great collector, pulling dust into stars, into galaxies and galaxies, into magnificent clusters. We assumed its pull was eternal, the ultimate arbiter of cosmic destiny. The entire universe we thought was locked in a tug-of-war with itself, with gravity, slowly inevitably winning the fight, perhaps one day pulling everything back together in a final fiery big crunch. But we were wrong. The universe isn't slowing down, it's accelerating. This revolutionary discovery was a profound shock to the system of cosmology, a result so counterintuitive it felt like a mistake. Yet the evidence written in the fading light of distant exploding stars was undeniable. Something was pushing back against gravity. Something was flooring the accelerator on cosmic expansion. This something is dark energy. It isn't a substance that exists in space like a strange gas or exotic particle. It appears to be an intrinsic property of space itself. Every cubic centimetre of the vacuum, even the most perfect emptiness you can imagine, seethes with a latent energy, a repulsive force that drives things apart. It is the universe's relentless exhalation. On smaller scales, like within our own solar system, or even our galaxy, this cosmic push is utterly trivial. The gravitational grip of the Sun, of the Milky Way's central black hole, of all the stars and gas clouds is overwhelmingly dominant. Dark energy's influence here is like the whisper of a ghost trying to halt a freight train. It's present, but completely inconsequential. However, when you zoom way out to the incomprehensible scales of the cosmic web, the balance of power begins to shift dramatically. The universe becomes a patchwork of gravitational kingdoms and desolate, empty frontiers. And it is in these frontiers, these vast gravitational deserts we call voids, where dark energy reveals its true terrifying power. Consider the Bootes void. Here matter is spread so thin that the collective pull of gravity is diluted to almost nothing. Across millions of light years, there is simply not enough stuff to hold the region together against the universe's intrinsic expansion. In this arena, the freight train of gravity has been replaced by a few scattered dust motes, and the ghost's whisper becomes a deafening roar. Here, dark energy is not fighting a strong opponent. It is virtually unopposed. And so, it reigns supreme. The fabric of space-time within the void stretches, and it stretches faster and more aggressively than anywhere else. It's not an explosion pushing matter away from a central point. It is a more insidious, more fundamental process. The very space between the few galaxies inside the void, and between the void and the great walls of galaxies surrounding it, is actively and continuously being created. This is the engine that powers the void merger hypothesis. Imagine two smaller adjacent voids separated by a tenuous filament of galaxies, a fragile cosmic fence. Inside each void, dark energy relentlessly pushes outward, stretching the space within them like a balloon being inflated. This inflation exerts an immense tidal stress on the filament caught between them. The galaxies in that wall are not just pulled by their neighbours, they are being physically carried away from each other as the very ground of space-time expands beneath them. The fence begins to break. The gravitational bonds holding the filament together are systematically severed by the swelling voids on either side. Slowly, inexorably, the filament dissolves. Its galaxies are pushed and pulled until they are assimilated into the larger superstructures on the far sides of the voids, effectively evacuating the territory between them. As the dividing wall vanishes, the two voids flow into one another, their immense volumes combining. Their individual identities are erased and a single more monstrous supervoid is born. This is not a gentle collision, it is a conquest driven by the fundamental repulsive energy of the cosmos. The Bootes void in this scenario is not just an absence of matter, it is a testament to the victory of dark energy over gravity, a region where the cosmic push has triumphed so completely that it has scoured 1 billion cubic light-year volume almost clean. It is a scar on the universe carved by the universe's own inherent desire to expand. Yet even this overwhelming engine of emptiness is not perfect. The cosmic eviction was not absolute. It left behind survivors, castaways. Within the unfathomable soul-crushing expanse of the Bootes void, adrift in an ocean of profound nothingness, a handful of galaxies still shine. They are the cosmic equivalent of shipwrecked survivors on a desert island, their nearest neighbours so fantastically distant they might as well not exist. For decades we knew of only a few, but as our surveys have grown more sensitive, the population has risen to perhaps 60 known galaxies. 60 islands of light in a sea of shadow, 1 billion light years across. And it is here, in this place of extreme isolation, that we have been given a gift, a perfect cosmic laboratory. What can these lonely galaxies, these cosmic hermits, teach us? To understand their significance, you must first appreciate what a normal galactic life is like. A galaxy like our own Milky Way lives in a bustling, crowded cosmic suburb. We are part of the local group constantly interacting with Andromeda and dozens of smaller satellite galaxies. We are forever feeling the gravitational nudges and pulls of our neighbours. Galactic life is a story of collisions, mergers and harassment. These interactions trigger ferocious bursts of star formation, warp galactic disks, and strip away gas, fundamentally shaping a galaxy's evolution. It's a chaotic, violent, and messy existence. The galaxies inside the Booty's Void, however, have experienced none of this. They are a control group in the grandest experiment imaginable. By studying them, we remove the noise of environmental influence and can witness the pure, undisturbed process of galaxy formation and aging. It's like studying human development on an island with only a single inhabitant. What happens when a galaxy is left completely utterly alone for its entire lifetime? The first clues lie in their star formation. While galaxies in dense clusters often experience a boom and bust cycle, where a merger ignites a brilliant but short-lived firestorm of star-birth void galaxies, appear to lead a more quiescent existence. They seem to simmer rather than boil. With no external galaxies to collide with and stir up their vast reservoirs of hydrogen gas, the fuel for new stars, their star formation, is likely a much slower, more sedate, and more sustainable process. They hoard their primordial gas, using it sparingly over billions of years. This might mean that while a galaxy like the Milky Way has already undergone its most productive star-forming eras, a void galaxy of the same age might still be gently glowing with the fires of youth. They are potentially living examples of a much earlier, quieter cosmic epoch preserved in the sterile environment of the void like a specimen in amber. They are cosmic time capsules offering us a glimpse into a path of galactic evolution our own galaxy could never have taken. This profound isolation has an even deeper impact written into the very chemical makeup of their stars. Every star is a nuclear furnace forging heavier elements from the primordial hydrogen and helium of the Big Bang. When massive stars die in supernova explosions, they blast these new elements, the carbon in your body, the oxygen. You breathe the iron in your blood out into the interstellar medium. In a crowded galactic city, this enriched material is constantly being mixed, shared and recycled through mergers and gas flows. Galaxies trade material, their chemical histories becoming blended and complex. But a void galaxy is a closed system. It can only enrich itself with its own recycled star stuff. There is no new exotic material flowing in from the outside. As a result, we expect these galaxies to be chemically simpler, more pristine than their counterparts in the cosmic web. Their metallicity, the astronomical term for the abundance of elements heavier than hydrogen and helium, should be significantly lower. Measuring this gives astronomers a direct window into the fundamental processes of stellar nucleosynthesis, untainted by the complex environmental factors that muddle the picture elsewhere. It's like comparing the complex soil of a continental rainforest with millennia of depositions from wind and water to the simple volcanic soil of a brand new island. Each tells a different but equally important story of formation. Perhaps most visually striking is their structure. The grand, majestic spiral arms of a galaxy are incredibly fragile structures. They are delicate density waves easily disrupted and torn apart by the gravitational tides of a close encounter with another galaxy. In the violent demolition derby of a galaxy cluster, pristine, undisturbed spiral galaxies are a rarity. Most have been warped, truncated, or completely shattered into irregular or elliptical shapes by repeated collisions. But in the serene tranquility of the void, there are no collisions. There is no gravitational harassment. As a consequence, many of the galaxies discovered within the Booty's Void are remarkably well-formed, almost perfect examples of spiral or disk galaxies. They are celestial fossils showcasing what a galaxy can look like when allowed to evolve in complete solitude, its beautiful pinwheeling structure unmolested for eons. They float in the darkness, gravitational gyroscopes spinning in perfect isolation, their delicate arms a testament to a life lived in peace. This presents us with a startling paradox. The most placid and undisturbed places in the universe are found inside its most extreme and desolate regions. These lonely islands of light, therefore, are far more than mere curiosities. They are Rosetta Stones for understanding the universe. Each one is a unique data point telling us about the fundamental physics of star formation, of chemical enrichment, and of structural evolution in the absence of external influence. They represent a baseline, a state of nature, for galaxies, that allows us to better comprehend the complex lives of their more cosmopolitan cousins, like our own Milky Way. They challenge our models and refine our understanding of the cosmic ecosystem. By observing what they are, we learn more about what we have become, but their importance extends even beyond the story of galaxies themselves. These tiny points of light have travelled for hundreds of millions of years, crossing the vast emptiness of the void to reach our telescopes. Their journey itself contains information. The light from these galaxies serves as a probe, a messenger that has passed through the very heart of this immense and mysterious structure. As it travels, its path can be subtly bent, its wavelength stretched not just by the overall expansion of the universe, but by the specific properties of the void it is traversing. Could the secrets of the void's true nature, and perhaps even the nature of the dark energy that inflates it, be encoded in these faint ancient beams of light? To find out, we must now turn our attention from the objects themselves to the long and perilous journey their light has taken to reach us. And so, having charted the ghostly coastlines of this impossible ocean of nothing, we find ourselves at the heart of the enigma. The terrifying emptiness we have traversed, this profound and cathedral-like silence in the cosmic choir, was not born from some late-stage cataclysm or the inscrutable work of a long-dead intelligence. Its origins are far more ancient, far more fundamental, woven into the very first syllable of time itself. To understand the giant void, you must understand that it was not carved out of the universe as we know it. In a very real sense, the universe as we know it was built around the void. The story of its creation is the story of everything. We must cast our minds back beyond the first stars, beyond the first atoms, to a moment when the entire observable cosmos was compressed into a space smaller than a single grain of sand. This was not a universe of structure or form, it was a cauldron of pure energy, a perfect uniform incandescent plasma. Yet perfect in the quantum world is a deeply misleading word. At this infinitesimally small scale, the fabric of reality itself is not smooth, but froths with uncertainty. It is a seething, unpredictable foam of possibilities where particles and energy can flicker into and out of existence for moments too brief to measure. These are quantum fluctuations, the universe's primordial heartbeat. Imagine them not as grand events, but as the faintest whispers in an otherwise silent chamber, microscopic ripples on a perfectly still pond. For every fleeting instant, a region became fractionally denser with energy, an adjacent region became fractionally more rarefied. These were the seeds of everything that would ever exist, and also the seeds of everything that would not. In that primordial soup, a patch destined to one day become the Booty's void was born from a flicker of quantum chance, a tiny momentary deficit of energy. It was a region infinitesimally less dense than its surroundings, a statistical anomaly so slight it was practically non-existent. In any normal state of affairs, this minuscule imbalance would have been erased in the next quantum heartbeat, smoothed back into the energetic whole. But what happened next was anything but normal. In the first trillionth of a trillionth of a trillionth of a second, the universe underwent a period of violent, almost incomprehensible hyperexpansion. We call it cosmic inflation. This was not an explosion in space, but an explosion of space itself. The universe did not just get bigger, it swelled exponentially, doubling in size again and again and again, faster than the speed of light itself. It was as if a cosmic megaphone had been placed against those tiny quantum whispers, amplifying their sound into a deafening roar that would echo through all of subsequent history. That infinitesimal crease in space-time, that microscopic region of slightly lower density, was grabbed by inflation and stretched. It was stretched beyond all recognition, expanded from a quantum fluctuation into a vast astrophysical scale region of slightly emptier space. Suddenly, the universe was no longer a uniform plasma. It was now a colossal canvas, still hot and dense, but imprinted with a faint ghostly blueprint of its own future. There were vast regions that were ever so slightly denser, and even vaster regions like the progenitor of our void that were ever so slightly more tenuous. The die had been cast. The stage was set for the second great architect of creation to begin its patient, deliberate, and relentless work over the next 13 billion years. That architect was gravity. Following the brilliant flash of the Big Bang and the dramatic inflation of space, the universe was still a remarkably homogeneous place filled with a near-uniform mist of matter and dark matter. But the seeds of structure, those inflation-amplified density variations, were there. Gravity, as you know, is a force of attraction. It is persistent. It is unforgiving. It sees even the slightest concentration of mass and begins to pull. In those regions blessed by the quantum lottery with a fraction more matter, gravity had a slightly stronger grip. Slowly, inexorably, it began to draw more material in. An atom pulled another atom closer. A cloud of gas felt the tug of a neighbouring cloud. Over millions of years, the process was almost imperceptible. But cosmology plays the longest of games. The rich got richer. Areas that started with a marginal advantage began to accumulate matter from their surroundings, their gravitational influence growing with every particle they accrued. The process began to snowball. You can visualize it as the formation of watersheds on a planetary scale. Rain falls almost uniformly, but tiny insignificant variations in the terrain guide the water. Trickles become streams, streams merge into rivers, and rivers carve their way to the great oceans. In the cosmos, the rain was the primordial matter and gravity was the terrain. The slightly denser regions acted like gravitational valleys pulling matter towards them. Over hundreds of millions of years, these valleys became deep gravitational basins. Matter flowed along unseen currents from the emptier regions, evacuating them and pooling into ever larger structures. What began as thin sheets of gas collapsed under their own weight. These sheets then fragmented, draining into long, winding rivers of matter that we now call filaments. And where these cosmic rivers met the true masterpieces of gravity's artistry took shape. Here in these chaotic, turbulent intersections, matter piled up in unimaginable quantities. The first stars ignited, blazing to life in the hearts of condensing nebulae. These stars clustered together, forming the first infant galaxies. Galaxies in turn were drawn into the gravitational whirlpools, merging and colliding, assembling themselves into the colossal clusters and superclusters that dominate the cosmic landscape today. This is the origin of the cosmic web, that luminous galaxy-studded scaffolding of the universe that we finally managed to map. It is the skeletal structure of reality itself, a testament to gravity's patient cumulative power. But in this grand story of cosmic construction, we have only told one side of the tale. For every region that was a winner in the gravitational lottery, there had to be a loser. What happened to those vast areas that began life with a slight deficit of matter? What became of the places from which all that material was being stolen? As gravity pulled matter into the filaments and clusters, it was simultaneously emptying out the spaces in between. These regions, like the one that would become the Bootes void, started with less. Consequently, their gravitational pull was weaker. They could not hold on to the little matter they had. Their neighbours, the burgeoning superclusters, were gravitational bullies siphoning away their gas, their dust and their dark matter, leaving them increasingly barren and desolate. For billions of years, this gravitational segregation continued. The cosmic web grew brighter, more concentrated and more complex. The spaces between the filaments grew emptier, darker and larger. The voids were not just gaps. They were an essential and co-equal part of the cosmic architecture. They are the quiet, expanding countryside that gives definition to the bright, bustling superhighways of the galaxies. Without the voids, there could be no cosmic web. They are two sides of the same cosmic coin, one forged in accumulation, the other in evacuation. This process alone, the simple and elegant physics of gravity acting on the initial quantum seeds, can explain the existence of voids. It can explain their shape and their relationship to the filaments that surround them. But it cannot by itself explain the sheer monstrous scale of the giant void. Gravity left to its own devices would create a universe of magnificent structures, but the voids between them would be significantly smaller. There was another force at play, a mysterious and ethereal influence that had been working in the background since the beginning, waiting for its moment to dominate the cosmic stage. To solve the final piece of this puzzle, we had to discover the universe's deepest secret, the fact that space itself is not passive. It possesses an intrinsic repulsive energy. We call it dark energy. For the first several billion years of the universe's history, gravity was king. The cosmos was denser, and gravity's attractive pull easily overpowered the subtle outward push of dark energy. The expansion of the universe initiated by the Big Bang was actually slowing down as gravity tried to pull everything back together. But as the universe continued to expand, matter became more diluted. The galaxies grew further apart and gravity's influence over large distances began to weaken. Dark energy, however, is different. It is a property of space itself. As more space is created, more of this repulsive energy comes into being. Its strength does not dilute. It remains constant, an ever-present pressure pushing the universe apart. Around 5 billion years ago, a cosmic tipping point was reached. The relentless repulsive push of dark energy finally became stronger than the attractive cohesive pull of gravity on the larger scales. The expansion of the universe stopped slowing down. It began to accelerate. This was a paradigm shift in our understanding of reality, a discovery that rewrote the final chapters of the cosmic story. And its effect on the great voids was profound. Dark energy is an anti-gravitational force. It works best where gravity is weakest. And where is gravity weaker than in the vast underdense and empty heart of a void? Inside the dense filaments and clusters, gravity still held sway, binding galaxies together against the cosmic tide. But inside the voids there was almost nothing to resist the push. Dark energy became a celestial blowtorch, a runaway expansionary force that took the already large gravitationally excavated voids and inflated them like balloons. They began to swell dramatically, pushing the surrounding walls of galaxies further and further away, growing ever larger, ever emptier. The rich got richer, and the poor, in a cosmic sense, became profoundly destitute. This is the final crucial step in the creation of the giant void. It began its life as a quantum flicker of less than average. It was stretched by inflation into a vast region of subtle underdensity. For billions of years, gravity patiently siphoned away what little substance it contained, drawing it into the magnificent Coma and Hercules superclusters that form its borders. And then, for the last 5 billion years, dark energy has been force-feeding its expansion, pushing its boundaries outward at an accelerating rate, scouring its interior until it became the monolithic, almost perfect vacuum we see today. The giant void, then, is not an anomaly. It is not a cosmic mistake or a hole in the fabric of space-time. It is an extreme yet perfect manifestation of the fundamental laws of our universe. It is the ultimate consequence of the interplay between the four great forces of our cosmos, the quantum uncertainty that provided the seed, the inflationary burst that magnified it, the patient gravity that sculpted it, and the mysterious dark energy that inflated it to its current breathtaking scale. This elegant, powerful narrative is encapsulated in what we call the lambda CDM model of cosmology. CDM stands for cold dark matter, the invisible mass whose gravity is essential for building the cosmic web. And lambda is the symbol cosmologists use for dark energy, the cosmological constant. This model, our standard model of the universe, does not just allow for the existence of voids, it actively predicts them. It predicts their shapes, their sizes, their distribution, and their relationship to the larger cosmic structure. And in this, the giant void transforms from a source of cosmic terror into one of our most powerful scientific tools. Its existence is not a challenge to our theories, it is one of their most spectacular confirmations. Because it is so vast and so empty, it serves as a pristine natural laboratory for studying the very forces that created it. The subtle ways in which the light from distant quasars is bent as it passes near the void's edge can tell us about the distribution of dark matter. The precise rate at which the void is pushing its surrounding superclusters away from us gives us one of our cleanest measurements of the strength of dark energy. We can test our models of galaxy formation by searching its barren interior for the few lonely galaxies that manage to survive there, like isolated island ecosystems. We point our supercomputer simulations at the lambda CDM model, we tell them to evolve a universe with our known ingredients, and they produce virtual cosmoses filled with structures that look uncannily like the one we inhabit, complete with their own giant voids. The void, once a symbol of our ignorance, a terrifying blank space on our map of reality, has become a lens. It is a cosmic magnifying glass through which we can scrutinize the faintest whispers from the dawn of time and the deepest, most powerful forces shaping the universe's ultimate destiny. By studying this magnificent emptiness, we are refining our understanding of the universe's past and sharpening our predictions of its far future. The monster in the dark has become our guide, its profound silence speaking volumes about the nature of everything. It confirms we are on the right path, that our story of creation from quantum seed to galactic supercluster is fundamentally correct. But within that confirmation, new more subtle questions begin to emerge. What else is this void showing us? What secrets still lie dormant within that profound and silent darkness, waiting for a new generation of explorers to ask the right questions? And so, we arrive here at the edge of the abyss, having crossed a chasm of space and time so profound it defies all human intuition. Our journey began with a bewildering map of the cosmos, a map that seemed to contain a colossal error, a flaw in the data, a smear on the lens. It was a blank patch, a region of profound celestial poverty stretching over 1 billion light years, where the grand, glittering tapestry of the universe appeared to have been torn away. We looked upon this great nothing, this giant void, and felt a primordial unease, the kind of vertigo one feels when staring into an infinite silent darkness. It felt wrong. It felt impossible. It felt like a violation of the very principles that stitch reality together, the universal expectation that where there is space, there must also be something to fill it. We were confronted not with an object or a phenomenon, but with an absence so complete, so incomprehensibly vast, that it challenged our most fundamental assumptions about the structure of everything. The universe we had always believed was a place of glorious chaotic creation, a cosmic ocean teeming with islands of light. But here was a desert, a vacuum on a scale that dwarfed galaxies, a silence that swallowed the echoes of the Big Bang itself. This initial shock, this confrontation with cosmic emptiness, has since given way to one of the most transformative revelations in modern cosmology. We have journeyed through the intricate computer simulations that first predicted such structures, watching as gravity, the universe's master sculptor, spent billions of years patiently herding matter into glistening filaments and dense jewel-like clusters. In doing so, it was not merely building the cosmic web, it was also carving out the spaces in between. We have learned that the giant void is not a mistake, it is not an anomaly, it is an inevitability. It is the other necessary half of creation, the yin to the brilliant yang of galactic superclusters. For every river of light there must be a watershed of darkness. For every celestial mountain range there must be a valley. The void is the universe's great valley, sculpted by the inexorable pull of gravity on everything outside its borders, a testament not to what is missing but to where everything else has gone. Its existence is a confirmation, a triumphant validation of our understanding of cosmic evolution, a shadow that proves the existence of the light. And yet to call it empty is a profound disservice to the subtle and beautiful physics unfolding within its depths. As we've seen, the void is not a true vacuum in the sterile laboratory sense. It is merely underdense. Within its fathomless expanse drift the loneliest galaxies in the universe, ancient and isolated systems that have evolved in near-perfect solitude. These are the celestial hermits untouched by the gravitational turmoil, the mergers, and the galactic cannibalism that define life in the crowded cosmic cities. They are pristine relics from a simpler earlier epoch time capsules containing clues about the primordial conditions of galaxy formation whispers from a time before the great structures had fully coalesced. Studying these lonely wanderers is like finding the first draft of the cosmic story, offering us a glimpse into the universe's untainted youth, a perspective shielded from the chaos of the cosmic metropolis where we reside. They are the quiet witnesses floating in the stillness, holding secrets that their more battered and bruised cousins in the filaments have long since forgotten. Their faint light travelling for eons across the immense emptiness is a message in a bottle, a story of survival in the most desolate environment imaginable. But the true significance of the void, the reason it has become one of the most crucial frontiers in our quest to understand reality, lies not in the few lonely galaxies it contains, but in the very fabric of space-time that defines it. Here in this realm of extreme underdensity, the eternal cosmic tug-of-war between gravity and dark energy finds its most dramatic expression. Throughout the universe, gravity works tirelessly to pull things together, building stars, galaxies, and clusters. It is the force of structure, of order, of accumulation. But opposing it is a mysterious, pervasive influence we call dark energy, a property inherent to space itself, a repulsive force that pushes everything apart. In the dense filaments of the cosmic web, gravity still holds the upper hand, its grasp strong enough to bind galaxies together against this cosmic tide. But here inside the giant void, the balance of power shifts dramatically. Here there is so little matter, so little gravitational attraction, that dark energy reigns supreme. The void is its kingdom. It is a cosmic laboratory where we can observe the effects of dark energy in their purest form. As you stand at its edge and gaze across, you are staring into a region where the expansion of the universe is not just happening, it is accelerating with an unnerving clarity. The space itself is stretching, expanding, and pushing the void's lonely inhabitants ever further apart, their retreat hastened by this dominant ghostly force. The void is in a very real sense the great cosmic exhale, the lung of the universe, where the deep, fundamental expansion of reality is made manifest. It is a place where the universe reveals its ultimate fate, a future of accelerating expansion and growing isolation. By studying the precise rate of this expansion across the void, by measuring the subtle distortions in light from background objects as it passes through this realm, we are probing the very nature of dark energy itself. Is it a constant, unchanging force, Einstein's cosmological constant? Or does it change over time, a dynamic field with properties we have yet to imagine? The answers are not written in the hearts of stars or the cores of galaxies, but here in the profound and revealing silence of the great nothing. This understanding has irrevocably transformed our perception of cosmic architecture. The voids are not passive gaps. They are active and essential components of the cosmic engine. They are the invisible scaffolding that shapes the visible universe. Their gentle, persistent outward pressure helps to shepherd galaxies towards the filaments, acting like a cosmic sheepdog guiding the flock. They are the source of the push that complements gravity's pull, a dualistic system of forces that has governed the cosmos for 13 billion years. Without the voids, the cosmic web would be a far more diffuse, less defined structure. The magnificent sharp filaments of galaxies we observe would be blurred, the dense clusters less compact. The universe as we know it, with its breathtaking contrast between light and dark density and emptiness, would not exist. These vast expanses of seeming nothingness are in fact the silent architects of cosmic beauty, the unseen hands that have sculpted the masterpiece we inhabit. They are the quiet counterpoint in the grand celestial symphony, the rests between the notes that give the music its structure, its rhythm, and its soul-stirring grandeur. And so we find ourselves looking towards the future armed with a new appreciation for this immense and enigmatic region. Our exploration of the void is only just beginning. The next generation of cosmic cartographers is already preparing to map these dark realms with a precision that was once the stuff of science fiction. On a remote mountaintop in the Chilean Andes, the Vera Sea, Rubin Observatory is poised to begin its legacy survey of space and time. For a decade, its vast mirror will scan the southern sky every few nights, creating a motion picture of the cosmos. It will chart the positions of billions of galaxies, tracing the edges of voids with exquisite detail and uncovering countless more of their solitary inhabitants. Its deep and wide-eyed view will allow us to create a three-dimensional map of these structures so accurate that we can measure the subtle ways in which their gravitational or anti-gravitational influence shapes the universe around them. We will be able to see not just where the voids are, but how they are growing, how they are influencing the flow of matter, and how their presence affects the cosmic microwave background radiation that fossil light from the dawn of time. Joining this quest from orbit high above the distorting veil of Earth's atmosphere, the Euclid Space Telescope and the Nancy Grace Roman Space Telescope will provide a different but equally crucial perspective. They are designed to be dark energy hunters. By meticulously measuring the shapes and distances of billions of galaxies, they will map the cosmic web and its voids across cosmic history, looking back in time to see how the battle between gravity and dark energy has evolved. They will use the subtle phenomenon of weak gravitational lensing, where the light from distant galaxies is bent by the matter it passes to weigh the universe. More importantly, they can detect the opposite effect, an anti-lensing signal, as light crosses the immense underdense voids. These telescopes will effectively take the universe's blood pressure, measuring the push and pull of cosmic forces with unparalleled sensitivity. They might even find something entirely unexpected. Is there a limit to how large a void can be? Could a void exist that is so vast, so empty, that it fundamentally breaks our cosmological models? The search is on for even larger, more extreme structures, anomalies that could point towards new physics, a deeper understanding of gravity, or a more complex and stranger reality than we have ever dared to conceive. And the James Webb Space Telescope, with its extraordinary infrared vision, offers another tantalizing possibility. It can peer into the deepest, darkest corners of the void, searching for the faintest, most ancient dwarf galaxies imaginable. These would be the true primordial relics galaxies that formed in the universe's infancy, and were immediately exiled into the emptiness their star formation quenched almost before it began. Finding these ghosts in the dark would be like cosmic archaeology, unearthing the building blocks of galaxies like our own, and testing our theories of structure formation in the most extreme environment possible. What secrets do they hold? What stories could they tell of the universe when it was just a fraction of its current age? Each new instrument is a new set of eyes, allowing us to see the unseen, to map the darkness, and to listen for the faintest whispers in the cosmic silence. We are on the cusp of a golden age of void science, turning our most powerful instruments towards the emptiest parts of the sky, because we now understand that within that emptiness lies the key to the universe's deepest mysteries. Ultimately, our journey to the giant void and back brings us to a place of profound humility. It serves as a stark and powerful reminder of the sheer, mind-numbing scale of the cosmos. Our entire galaxy, with its hundreds of billions of stars and countless worlds, is but a single grain of sand on an infinite cosmic shoreline, and our local group of galaxies, a small gravitationally bound family, is itself just one tiny part of the Laniakea supercluster, a single glistening thread in the cosmic web. We live in the suburbs of creation, a place of immense density and activity, and for most of history we mistook our busy neighbourhood for the entire universe. But the void teaches us otherwise. It shows us that the majority of our universe is not like our home. Most of the cosmos is this vast, silent, expanding darkness, punctuated by lonely islands of light. It reorients our perspective, forcing us to confront the reality that our existence is a product of a fortunate cosmic anomaly, a localized victory of gravity over the encroaching emptiness. The void is not a place of fear, but a canvas for contemplation. It is the ultimate expression of cosmic solitude, yet it is also the framework that allows for connection, for the formation of the great galactic rivers that flow across the heavens. It is a physical manifestation of the boundary between something and almost nothing, and its existence is woven into the very fabric of our own. We are here because matter clumped together, which means by definition that voids had to form. Our being is predicated on their existence. To understand the void is to understand the fundamental architecture of our home, to appreciate the delicate balance of forces that allowed a planet like Earth to form a sun to ignite, and for us to emerge from stardust and gaze back out at the cosmos, asking these very questions. It is a humbling yet empowering realization. The story of the giant void is the story of science itself. It's a tale of finding something that shouldn't be there, of challenging assumptions, of turning a puzzle into a tool, and of transforming a terrifying abyss into a source of profound knowledge. It reminds us that our map of the universe is still largely unwritten, with vast dark continents waiting to be explored. There will be other voids, other mysteries, other phenomena that will initially seem to violate all logic. But each one is an invitation, a challenge from the cosmos to look deeper, to think harder, and to push the boundaries of our understanding ever outward. The quest to comprehend this universe is a journey without a final destination. There is always another layer to peel back, another shadow to illuminate. The giant void in all its silent, majestic, and incomprehensible grandeur is not an end to the story. It is a solemn, beautiful promise that the grandest discoveries still lie ahead of us, waiting patiently in the magnificent and inspiring darkness.